Control system modeling in the frequency domain, lecture 2, transfer functions. So at the end of this lecture, you should be able to understand how transfer functions are applied in engineering. You should be able to model real-world mechanical and electrical and control system using transfer functions. And you should be able to analyze and interpret system responses using MATLAB and Simulink. So in this lecture, we're going to introduce the Laplace, the transfer function. And in subsequent lectures, we're going to take a look at electrical, mechanical systems, and then kind of a combined system. But in this particular lecture, we're just going to define what a transfer function is. So a transfer function, in this case, we'll call it G sub s. Remember, s is frequency, and G is, it could be H, it could be F, it could be whatever. But typically, a lot of books, including our own, start off using G or H as the transfer function. So the transfer function relates the output of a system to its input, and it's in the Laplace domain. That's why it's a function of S. So it's simply a tool for analyzing system dynamics without solving differential equations directly. So it's a ratio of the output to the input. So later on, we'll introduce two key properties of transfer functions. We really won't touch on them in this lecture or the subsequent lectures, but in later chapters, we'll focus on these specific properties. One is what's called poles and zeros. We'll be able to find those. Those will tell us a whole lot about how stable the system is and how it responds. We'll also look at what's known as steady state gain. This tells us how the output scales with input. So let's take a look at a simple mass spring damper system with initial displacement x acted on by an external force F, small f. Let's also assume that the initial displacement and velocity at time 0 are both 0. So from the dynamics, we also understand how to model the system as a differential equation. We have mx double dot plus cx dot plus kx equals our function of time, our force function. So let's take the Laplace transform on both sides of the equation. So on the left-hand side, we have m times the Laplace transform of x double dot. So looking back at our Laplace transform table, we had a differentiation rule that said the Laplace transform of a derivative is s times the Laplace transform of the function s, minus the function evaluated at time equals 0. Well, in our case, we're taking the x double dot, so our Laplace transform is going to be s squared times capital X as a function of s. And since our velocity is 0 at time 0, this second term for us is 0, so we don't include it. The next term is c times the Laplace transform of x dot. So that's going to be c as a constant times s times capital X. And again, the initial displacement is 0, so that this term goes away. Plus k times the Laplace transform of x is simply capital X. On the right-hand side, the force function turns into capital F times a function of s. Now we can simply factor out capital X from all three terms on the left-hand side. Find this equation here. So continuing on from our previous slide where we factored out the capital X from all three terms, we can now solve this for the transfer function, X over F, capital F. So again, this is our transfer function. It's always written as the input divided by the output. So, in future lectures, we'll learn more about how to analyze this transfer function, plot it, and determine its properties. Here's some homework for you. You don't have to turn this homework in, but this homework will be Very useful if you did it before the next exam. So here, we're going to take the previous equation that we developed, and we're going to actually solve it in MATLAB. So here, we're going to give the mass of 200 kilograms, uh, a constant C of 1500 newton seconds per meter, a spring constant of 20,000 newtons per meter. We solve for this transfer function. So here, I show you how to write this transfer function in MATLAB. Then we're going to plot this transfer function as what's known as a step response. So this is a what's known as a quarter car model of a damper system that would be on a tire, car tire. So here, if you traveling down the road and you hit a bump in the road, that's the step function. It's a kind of like a jump. Then when we plot this, it'll show you what happens to the car. As you can imagine, the car will vibrate around and eventually come to a steady state. And so this is a good model for that. But I want you to run this code and email me a graph of the um, that MATLAB produces. All right, I'll see you in the next lecture.